LoRaWAN devices utilize narrowband communication to save energy. When you have thousands of them deployed, it becomes difficult to get the location by hand. You may need some radio-based technology to track your devices. However, conventional radio-based LoRaWAN localization does not perform well as narrowband signals have poor resolution. In this paper, we propose Seirios leveraging multiple channels to improve the accuracy for LoRa indoor and outdoor localization. First, let's have a look at the state of the art. LoRaWAN localization accuracy is poor. We take the data from the white paper. It says our SS-based technology could achieve only 1,000 to 2,000 meter accuracy. Of course, it was measured with a coverage up to several kilometers. We did a similar evaluation with our test bed, which is 100 meters wide. We see the result is not satisfactory. A major bottleneck is a multiplier effect, which has been proposed by many previous research. Previous research also suggested that to use super resolution algorithm to mitigate the multipass effect for wideband, like Wi-Fi based localization. There was no previous research about super resolution algorithm for LoRaWAN because LoRaWAN is narrowband, but it inspired us to use super resolution algorithm for LoRaWAN if we have multiple channels stitched together. However, there are some challenges. First, unsynchronized non-overlap LoRaWAN channels, and the second is insufficient resolution. If we would like to improve the localization accuracy, we need to solve these challenges first. Compared with the later work, we see that many radio technology with wideband can achieve accuracy within a meter, while LP1 technology with narrowband can only achieve accuracy of several meters. And the table 2 compared OWL and Seirios. OWL is latest work about LoRa localization, which was presented last year. OWL and Seirios share a common idea that to improve the accuracy, you need to improve the bandwidth. However, they propose different technique. OWL synchronize the phase of multiple base station, while Seirios synchronize the phase of multiple channels. They look like a dual problem that try to solve the same problem from a different perspective. And we see that Seirios use less bandwidth and less localization time and less packet exchange, which can save a lot of energy to maintain the low power for the LoRaWAN devices. And OWL could support a wider range than Seirios, but they do have a similar performance. Before we present the design of Seirios, we need to look into the physical layer of LoRa packet in case some audience does not have the background. Here is a typical example of LoRa physical layer. The horizontal axis is time, and the vertical axis is the frequency. We see that LoRa utilizes linear upchirp to encode its data. At the very beginning, you see LoRa has an identical linear upchirp as its preamble. There are 8 linear upchirps, which can help us in CSI estimation. Okay, now it's the main course, the design of Seirios. Seirios is designed to explore multiple LoRaWAN gateways to locate a transmitter. The approach that we use is similar to triangulation, but we made some improvements. First, I will show you the data that we use for localization. Of course, that is CSI, the channel state information, which has been widely used in Wi-Fi literature. CSI represents how signals at a certain carrier frequency propagate from the transmitter to the receiver, which has rich information about the multipass. LoRa CSI can be obtained by comparing received preamble with a predefined preamble, that is the linear upchirps. A trick that we use here is to sum up the repeating upchirps in the preamble to improve the signal to noise ratio for CSI estimation. As we all know that LoRa packet much below the signal to noise ratio could be decoded. Or for localization, we need a packet with high signal to noise ratio. Unlike Wi-Fi signals with CSI for each subcarriers are measured at the same time, the CSI for a LoRa channel is measured individually because you need to send a packet to measure the CSI for one individual channel. So if you would like to measure the CSI for multiple channels, you have to send the packet for each channel at different times, so they are not synchronized. But you need to synchronize them before you could use them for super resolution algorithm. Here I show you an example how the out-of-sync packet looks like. The horizontal axis is the frequency and the vertical axis is the phase. If they're not synchronized, you will see the random phase introduced between two packets. But theoretically, the overlapped part should be the same. So we can use the theory to synchronize multiple channels. So we get the figure B. We call this interchannel synchronization. But if you check with the LoRaWAN protocol, you know that there's a gap band between the adjacent channels, so you don't have overlap channel, which could help you prevent interference. However, we see that the frequency change is only like 200 kilohertz, which is not that much. So we choose to make a bridging channel by averaging the phase of two adjacent co-phase channels. And we can use the generated channel to synchronize multiple channels. You may question the effectiveness of the approach because the synthesized bridging channel may not be the exact overlapped channel. So we did a micro benchmark to show that the error introduced by the bridging channel can be ignored and the overall performance is acceptable. Since we already have the synchronized channel, we'd like to choose the super resolution algorithm for localization. Many researchers suggest to use angle arrival time flight joint estimation, like the music algorithm. In practical, we need to search the time flight, and in the pseudo spectrum, we will see a peak which shows a path. However, for LoRa, even you stitch multiple channels together, you only have 1.6 megahertz, and the raw resolution is something like 187.5 meters, which means that distance difference less than that number indistinguishable. And in the pseudo spectrum, you'll see those paths emerge into one peak, which is far away from ground truth. So you cannot estimate the time of flight directly. And even worse, that if you have a wrong time of flight estimation, it will influence the angle arrival estimation. So we have to avoid using a time of flight estimation for direct path resolution. We can only use the angle arrival, which is different from previous research. However, we choose to use aspirate. For example, if we have 8 channels and 2 antennas, we could solve with a conventional aspirate, we can solve 4 multipasses. But if we use a conjugated aspirate, we can solve 2 more passes, add up to 6 multipasses, which is 50% improvement. For the details and the mathematical deductions, you can check our paper. Now we have the angle arrival estimated, and we have to merge multiple APs. We use the multiple AP fusion to locate the transmitter. Here we define a likelihood function with Gaussian distribution. And we, with some empirical parameter, we could draw a figure on the right, which shows the likelihood for the path, no matter whether it's a direct path or a reflector, given a specific angle arrival. And then we translate this likelihood function into a heat map. And on the heat map, each point indicates the likelihood of that point as a transmitter. Figure 1 shows that if you have only one figure, you have so many possible positions of the transmitter. If you add one more gateway, the likelihood are merged, so the candidate will be reduced. And if you have a third one, you have less candidates. You have fourth one, wow, there's only one. And that is very close to the ground truth. You did the right estimation. Okay, to this end, I summarize our design. We need to synchronize the channel to get a synchronized CSI. And then we use conjugate aspirate for angle arrival estimation. And step 3, we use the heat map with likelihood for multiple AP fusion, and we get the location, the transmitter estimation. Then comes the engineering part. We implemented 4 prototypes with software-defined radio and the Raspberry Pi. Those software-defined radios have 2 synchronized antenna. And on the Raspberry Pi, we implement our program with GNU radio out of tray. We also use SIMD to accelerate the processing for those data, so those programs could detect and calibrate the CFO and compress the data in real time and upload it to the cloud. In the cloud, we implement a synchronization algorithm with super resolution algorithm to utilize multiple AP fusion to localization estimation. Before an end-to-end evaluation, we first did a micro benchmark to see how accurate the conjugate aspirate can achieve. We also evaluate inter-channel synchronization algorithm and find that the error introduced by non-overlapped channels has a little effect on AOA estimation. We conduct the outdoor evaluation on campus. Due to COVID restriction, it is already the largest place we can find to deploy our testbed. We also did the evaluation indoor in our laboratory. In the laboratory, we do have so many reflectors and blockages, so it's a normal, typical multi-pass environment. The result is satisfactory. And we compare conjugated aspirate with AOA TOF joint estimation and the baseline. The baseline that we've chosen is time difference of arrival. It's a naive approach to get angle arrival by comparing the time difference of arrival of 2 synchronized antenna. And the AOA TOF joint estimation have little improvement, while our conjugated aspirate could achieve about 40% improvement. So error is reduced by about 40%, both indoor and outdoor. We also compare our approach with other assets. The improvement is obvious. And for more details of our evaluation and findings, please refer to our paper. And the result of RSS and the TTOA draws straight back to the very beginning, to the motivation. We know that we made the achievement that we propose a new algorithm to improve the localization accuracy. In the end, I would like to conclude my presentation with our contributions as summarizing as 3A. A novel interchannel synchronization algorithm by exploiting the unique structure of the LoRa physical layer. An improved algorithm adding the conjugate of the channel state information to improve the ability for solving more multipaths. A prototype of Seirios with software-defined radios to achieve 41.6% smaller error than the baseline approaches. Thanks for listening.